the test.
No win.
Are you reading the board behind me? You see when the test is? No or yes? So you don't see here where it says conceptual chemistry, unit 4 test on the 21st. Come on. All right. All right. So take a look at the board, ladies and gentlemen. That's what we're going to be doing today. Just give me a minute to get attendance, and then we will get going. All right. No Jose. No Damien. All right. Greg, headphones, please. Nico, headphones, put them away. Thank you very much, gentlemen. Okay, so today we're going to do a few different things. Actually, I got some models. We're going to make some models today of some hydrocarbons and some alkanes, and we're going to look at those. And then tomorrow we're going to do a tensile strength lab. I don't know if we'll get it started today or not. But our reminders down at the bottom here are kind of important. Number one, ladies and gentlemen, Thursday is the last day for any late or missing work that you want to turn in, that you want to get credit for to try to pass the class or to improve your grade within the class. On Friday of this week, we'll be taking our Unit 4 test. It will not be a long test. It will be a little bit shorter because we only had a couple of weeks worth of stuff. But we will do that on Friday, ladies and gentlemen. And then next week, Thursday, is your final exam in here, and that's, that's next week, Wednesday, not Thursday. That is the right date. That is the wrong day of the week for you. Come on. Okay? So that is next week, Wednesday. I'm sorry, that is not next week, Thursday. Your final is at 9:30 a.m. or 7:30 a.m. until 9, first hour of the morning. So we'll talk about that as we get closer to it. Okay? But we are going to today talk about hydrocarbons and alkanes and a little bit of that. But my question of the day for you today, you have 5 senses. You have your sense of smell, you have your sense of sight, you have your sense of hearing, you have your sense of taste, and you have your sense of feeling. If you had to lose one of them, which one would you lose? Which one would you be willing to give up? Which of your 5 senses would you be willing to live without for the rest of your life?
Wait, could seeing also be a sense?
Seeing is a sense. So seeing, hearing, smelling, tasting, and feeling. Those are your 5 senses. What's that? See, I thought about that as well, too, because I thought, okay, if you touch something but you can't feel it, would you feel pain? I don't know, that's up to you, I guess, in this question. But now, here's the next question is, even if you can't feel pain, could you still burn your hand if you put it on something hot and you just not know you're burning your hand? Yeah. We're making the rules up for this question as we go, so you can make them any way you want.
Oh, right. Touch. Yeah, touch.
So if you're talking about your sense of touch, your sense of feeling, okay, if you were to grab something hot, if you were to grab something sharp, you wouldn't feel it, right? But the question is, would it still do damage? I don't know. I'm making a movie about that. Yeah, it's the new movie. It's called Novocaine.
Yeah.
The guy can't feel any pain or something.
Yeah.
So,
I mean, it was still like burn. It was still like burn.
but like he got shot and he couldn't feel it. He got shot and he could pull the bullet out or something like that.
Gun was in like boiling oil too.
I've just seen a little bit of the scenes from it. That's not the reason for the question. I just had this question before. So, what sense would you be willing to give up if you could give up a sense? If you had to give up a sense, you have to give up one. You give up touch. You're okay not feeling anything again.
Yeah, like if I'm in a fight, I don't need to feel anything.
Okay. Okay. So then you're also going with the fact that that sense of touch will apply to your entire body. Okay. Okay. You can make it whatever rule you want. It's your rule. You can do whatever you want.
Would it also mess with your sense of taste?
No, it would not. You'd still be able to taste food.
All right.
You're just giving up one sense.
All right.
Okay? Alexander, what sense are you giving up if you have to give up a sense?
Hearing.
Hearing?
Can I be as one?
Gotta be both. Gotta be both. You're giving up the whole sense. So it's not like you could hear out of one ear and not out of the other. Touch? You give up your sense of touch. Adam? Okay. All right. Great. Well, you have to. You're gonna lose one anyway. So what do you think what would your choice be? If you had to pick one, which one would you pick? Okay. All right. Can you?
No.
See, I think that's the one that I would probably give up too.
Which one?
Sense of smell.
Smell.
Smell. Not being able to smell things again. I think of all the senses, that would be the one that I would probably give up as well. Natalia? Smell? Oh, sure. Now you're just going to go right along on the coattails, huh?
I mean, personally, if you're smelling, you might like this is 60%. Like when you're eating 60%.
I understand that. I understand that, but again, I guess I would give up that sense of smell rather than not being able to feel anything again.
What if you're eating rotten food, but it doesn't look rotten, but you can smell it?
Well, I guess you're not going to know, are you?
Yeah.
So,
you vomit.
What if your hand is sitting on a hot oven and you can't feel it because you have no feeling of touch?
I just wouldn't be that. I just be careful with it.
Well, I would be careful with what I eat then.
And you really can't be that careful with it.
Sure you can. I don't eat things that are rotten now. And I don't even need my sense of smell to know that because I know how long I've had things in the fridge and things like that. So, Jesus?
I guess
Touch? Okay. Nico?
I said touch, yeah.
Touch? All right. Fantasia? Which sense are you giving up if you have to give one up?
Touch.
Touch? Why?
Because I don't like feeling pain.
Okay. Don't like feeling pain, so hopefully that would help with that. Okay. All right. Evelyn? Taste? Okay. Okay. Heavenly? Smell? See, I think smell and taste would be the first two I would give up. Probably then followed by sound, touch, and then sight. Sight would be the last one. Sight would be the one I wouldn't want to lose. Yes?
I think the sense of taste would be a bad one to lose because I mean everything's just gonna taste plain and
I understand that. But again, I don't want to lose my sense of sight. I want to be able to see things. I want to be able to drive. I want to be able to do things. So that one I'm not losing.
Yeah.
Okay. My second one that I don't want to lose is I don't want to lose the sense of feeling. I want to be able to touch things. I want to be able to feel things. I want to be able to have that sensation. Okay? So the first one that I would choose to lose again would be smell. Second one would be taste. Third one would be sound. Again, It's not that I want to lose any, but if I had to lose them, that would be the order that I would want to lose them in. So, personal preference, okay? So that's just me. All right, ladies and gentlemen, what I need you to do is open up your EISN. And I want you to get to this slide, slide number 23 real quick, ladies and gentlemen. Now, do I have all of the notes in there on that slide for you? I need you to get to this slide, please, ladies and gentlemen, and tell me if I have everything in there, because if I do, I'll just populate it right away. But if you've got to copy it down, I will go more slowly. So on slide 23 in your notes are the differences between structural and electron dot diagram models in there. Yes? That's all in there? Okay, good. Thank you very much, Natalia. All right. So a structural model is a model that shows how the atoms are arranged in a compound. One of the things that we're going to look at today is when you make models, is there only one way to put them together, or are there multiple ways to put them together? That's one of the things that we're going to look at today, and we're going to use some model kits that I have to help that. Because there are times where we need to look at what the structure of something looks like, because structure is important. There are more than one way to put the same combination of elements together, ladies and gentlemen. And when you do that, you need a structural model to show you how they're actually put together. Okay? We use a dash to represent a bond. Now, please remember, carbon can form 4 bonds. Hydrogen can only form 1. And we are talking about hydrocarbons. We are talking about a combination of carbon atoms and hydrogen atoms together. So the carbon has to be the main part because it can form 4 bonds. And then the hydrogen basically just fills in what's left over. But when we draw them, we use a dash to represent a bond. We'll explain the difference in an electron dot model in just a minute. What that bond actually is a pair of shared electrons. 2 atoms, each atom gives up 1 electron to make a bond, to share their electrons with another atom. Why? Because they don't want to gain or lose them. They both want to get more electrons, so the way they solve that is by sharing their electrons. And it gives them both electrons that they didn't actually have. Okay? A structural model allows you to tell something called an isomer apart, and we're going to talk about that in just a few minutes. Okay? An electron dot model is a model that shows how the atoms are arranged in a compound. It is exactly the same thing as a structural model. The only difference between it is it uses 2 dots to represent a bond instead of a dash. So electron dot actually shows the electrons between 2 atoms. Okay? In a structural model, they use a line to represent the bond. Electron dot, they use the 2 dots to represent the bond. It is a pair of shared electrons, same as it is here. Okay? And it allows you to tell isomers apart. It allows you to tell different structures apart from the same combination of things. Okay? All right. So these, ladies and gentlemen, are some structural formulas. But what I want you to do first is come up here and grab one of these model kits, ladies and gentlemen. So come up here, grab one of these model kits, take it back to your desk with you.
Is there only one per table?
1 per person. 1 per person. Okay. So when you open it up, ladies and gentlemen, these are called a ball and stick model. That is the name of them. Okay? When you look inside, you're going to see a bunch of different spheres. You're going to see a bunch of different colored spheres with different amounts of holes in them. Then you're also going to see the sticks. And there are short sticks, or I'm sorry, long sticks, and there are short sticks. Okay? These sticks can be used to bond 2 things together, to make a bond between 2 atoms. There are also springs in here. We will not be using these springs today, but I will show you what they are for. So first thing, take out one of the black spheres that is in there, ladies and gentlemen, and tell me how many holes are in the black sphere, please. 4. This represents a carbon atom, ladies and gentlemen. And the reason there are 4 holes in this black sphere is because carbon can form 4 bonds. So in other words, you can take a stick and place it in one of the holes. Now, if you use a long stick, you can then put another black sphere on there. And now you have made a 2-carbon chain. If you use a short stick, you should then take in a yellow sphere. And when you look at the yellow spheres, how many holes do they have in them? 1. They represent a hydrogen atom. So right now, this is C1H1. 1 carbon and 1 hydrogen. But the carbon is not stable. Why? Because it has 3 holes that are unfilled. That is 3 unpaired electrons that have yet to be part of a compound. So what I want you to do is take 3 more short sticks, put them in there, and then take and add 3 more yellow spheres. Now you do not need to cram this on together so tight that you are unable to get it apart later. All you need to do is put this together so that everything can stay in its place. Now, this is not a perfect model kit. What I mean by that is, even though some of the sticks, they're all the same length, some of them you may not get as close to one another, and some may appear to be closer to one another, but that's okay. Okay? That, ladies and gentlemen, is a model of the simplest alkane that you can make. That is a model of what is called methane. CH4. 1 carbon, 4 hydrogens. Now, if we think about it, each one of these sticks represents 2 electrons. 2 electrons. So around that central black sphere right now, there are 4 sticks. That means that there are 8 electrons around that central atom.
I got a question.
Shoot.
Is there a reason why some of them are longer than others?
Yes, I told you that was for a carbon-to-carbon bond, not a carbon-to-hydrogen. So you should be using the shorter sticks right now. Okay? So, this, ladies and gentlemen, again, is the compound methane. The simplest hydrocarbon you can make. 4 bonds around the central atom of the carbon means the carbon atom is stable. 1 bond with the hydrogen atom means the hydrogen atom is also stable. So everything in this compound is stable, ladies and gentlemen. Everything is stable. Okay? So this is the simplest hydrocarbon there is. Now, this is the way that they will draw this hydrocarbon if you were a chemist. There are multiple ways of doing it, but this is one. So they will take all right, so they will draw your carbon in the center just like that. Let me make that a little bit thicker. So there is your carbon atom. Then they will show a hydrogen off to the side, to the bottom, to the other side, and to the top. So what this means right now, ladies and gentlemen, is that there are 8 electrons or 4 bonds around the carbon atom. Okay? And there are 2 electrons or 1 bond for each hydrogen atom there is. And that's the maximum that they can make. That makes everything stable. Now, when you look at this, does this look like a cross like it's shown up here? When you look at this model, do you think it looks like a cross, kind of like it is shown here? No. But this is a two-dimensional drawing, ladies and gentlemen. Okay? That means that it shows X and Y. There's no way for it to show coming out of the screen that you are going back away. Well, if you hold this model like this, now you got the up and the down and the center, and you've got the three going across. So yes, this is a good representation of this model, but what it can't do is it cannot show you that some of those things are going away from you and some of them are coming towards you like they would like this here. Okay? All right? Questions? Take one of your yellow ones off. Okay? Take a long stick and put another carbon in there. And then these three extra holes on this carbon, again, fill them with 3 short sticks and 3 hydrogen atoms. And now you've got another model, ladies and gentlemen. Okay? Now you've got another model. So this model here, ladies and gentlemen, had the formula CH4, and we called it methane. By the way, ladies and gentlemen, methane gas, very flammable. Methane gas is produced by any living creature when it decomposes. But also, methane gas is produced by any living creature when you fart. This is the gas that is created when you fart. Now, be it a farm animal, be it your dog, be it your cat, be it you, this is a gas that is created when animals or living objects fart. Okay? Yes, it is burnable. Okay? It is burnable. But also, if you've ever driven past a landfill, landfills will have pipes that are coming out of the ground. And occasionally you will see flames burning from those pipes. Those pipes go down in the ground, and as garbage and other organic material, scrap food, waste that you throw away, go into the ground in a landfill. They decompose and they make this methane gas. Now this methane gas is very flammable. It is burnable. Okay? And if you do not burn it, what will happen is it will build up in big pockets in the ground and it will explode. Well, they don't want that in a landfill. So they have pipes that go down in the ground that allow this gas to come to the surface. And when the pipe, there's a sensor on the top, when it senses methane gas coming out, it burns it right away. Yes?
Why don't they just use it for energy?
Well, they do in some places. They do. There are some farmers who will take their manure, the waste from the cows, put it in a pit, and they will create this methane gas. They will then take that gas and use that to power their farm. They will use it to create electricity. They will use it to create heat, things like that. The problem is it's very expensive. It also isn't the most energy efficient. So the farmer has to invest a lot of money to create a system to recapture this stuff. But there are some who do. There are some large farms who do. Okay? So, that's methane, ladies and gentlemen. Now we've taken and we've added a carbon to it. So now we've added a second carbon. Well, can we hang on and get this one done first? Okay? Chill out for a minute, please. So now we've got 2 carbons connected. Okay? And again, at each end, we have 3 hydrogens, and the reason for that, ladies and gentlemen, is so that the hydrogens can fill up the bonds around carbon. So again, in this case, each carbon still has 4 bonds that come from 8 electrons, which means it is stable, ladies and gentlemen. Okay? And each hydrogen has 1 bond and 2 electrons, which make it stable. So again, everything is stable again, ladies and gentlemen. In our compound, everything is stable again. But again, you're looking at this and you're going, okay, I don't quite get the above, below, ends. Well, again, this is probably as close as I can do it for you. It isn't perfectly up and down, but you still have up and down here. You still have the 2 ends here. So again, this model is a pretty good model. Okay? This model is a pretty good model of what this looks like. Now, because these are what are called single bonds, ladies and gentlemen, they can twist and turn around there. Okay? But what happens is these atoms here try to get as far away from each other as they can, ladies and gentlemen. And what that means is they are going to line themselves up so that they are as far away from each other as they can. Okay? But again, it's another stable compound. The name of this compound, ladies and gentlemen, is called ethane. Ethane has the formula C2H6. That is the formula for ethane. Questions? All right. Let's do what Solomon wanted to do. Let's add another carbon. So take off one of your hydrogens. I don't care from where. Put a long stick in and put another black sphere to represent a carbon. When you're done with that, again, add a few more hydrogens to your compound with these short sticks. Okay, still sign in, please, sir. So, again, ladies and gentlemen, we now have a molecule that looks like this. Okay, Jasmine, if you want a model kit to build some models, they're here. Same thing for you, Jose. Okay, so now we've built an even longer carbon chain. But again, same rules are still applying. Every carbon atom needs to have 4 bonds. Okay? Every carbon atom needs to have 4 bonds. No. Take the whole kit. No, not mine. The kit next to it. Sorry, sir. There you go. Thank you. Okay? All right. So now, ladies and gentlemen, let's take a look at our next one. Our next one, we get 3 carbons in a row. Carbon slash carbon slash carbon. And now we get hydrogens. Again, above and below each one until we get 4 bonds around each carbon. Now, this is the first time, ladies and gentlemen, that we had enough carbons to where we have a carbon in the middle. Okay? So this carbon is bonded to this one and to that one. That's 2 bonds. And that's why it only has room for 2 hydrogens with it. Because it's not on the end, it only has room for 2 hydrogens, where these have room for 3. But again, our rules are still holding. What do I mean by our rules? Well, every carbon atom still has 4 bonds. And it means that it has 8 electrons. And therefore, it is stable. Every one of these carbons. This one here, 1, 2, 3, 4 bonds. The one in the middle, 1, 2, 3, 4 bonds. The one on the end, 1, 2, 3, 4 bonds. All stable. Every one has the maximum amount of hydrogens that it can hold. Every one, ladies and gentlemen, has its 4 bonds around it. Now again, hydrogen only has 1 bond, which is okay because that is 2 electrons, and that still makes this hydrogen stable. It just does it with fewer electrons than the carbons do. Okay? This, ladies and gentlemen, is something most of you probably have in your home. This is called propane, ladies and gentlemen. That is the stuff that is in your gas grill, probably outside back on your patio. Okay? Maybe you have a propane heater that you take if you go ice fishing or you go somewhere outside in winter, or if you have one in your garage to warm it up so that it doesn't get quite so cold if you have to work in your garage. Propane, some people cook with. Now, again, if you live in the city of Green Bay, you probably have natural gas. That is a combination of some of these other gases. It's some methane, it's some butane, it's some ethane, okay? But if you live out in the country, you will have you'll see big white tanks by homes. Those are propane tanks. They use propane to cook. They use propane to heat their water heater. They use propane to possibly heat their furnace or run their furnace. They use propane for possibly drying their clothes. People in the city use natural gas for those things. Okay? But propane is this C3H8. All right. Now, here's where it starts to get a little bit more interesting, ladies and gentlemen. Okay? We're going to take and add one more. But before we do, this model that I just wrote here, this one, there will be a shorthand way for scientists to write this model, to draw this model out. Scientists do not like to draw all of these carbons and hydrogens. It takes too much of their time. So they will make a model, ladies and gentlemen, that looks like this. Sorry, that's a terrible rendition of it. They will draw that. Now, if you're sitting there wondering how this and this can be the same, ladies and gentlemen, this is this. Hydrogens above and below every carbon. The carbons in a straight line, 2 hydrogens at the end. This is this, just looking at the carbons. Okay? So this kind of V, upside down V shape, is showing you this part of the model. And organic chemists will only do this, and they will understand that in every one of these corners, every one of these end spots, there is a carbon atom. And that each of them make 4 bonds. So this one on the end here has 1 bond here, it'll make 3 more to hydrogen. This one in the middle has 2 bonds, it'll make 2 more to hydrogen. And this one on the end has 1 bond, it'll make 3 more to hydrogen. All right. So now you're going to take and you're going to add 1 more hydrogen or 1 more carbon to this. And again, ladies and gentlemen, you are going to take and you are going to put in 3 more hydrogens so that we fill up all of our bonds.
I have a question.
Shoot.
Why do we keep on filling it up with hydrogen if we have other ways that we can fill it up?
One more time, again, a little bit louder, please, Fantasia.
Why do we keep filling it up with hydrogen if we have other?
Because for these compounds to be stable, Every hydrogen or every carbon atom needs to have 4 bonds. If it doesn't have 4 bonds, it is not stable. Okay? So hydrogens go and fill in those extra electrons that are around the carbon, those extra spots for bonds, so that everything can become stable. Okay? So this carbon atom right here, without these 3 hydrogens on it, it would not be stable. It has 3 pairs of electrons that it isn't bonded to anything, and therefore it's not going to be stable that way. But when these hydrogens come and fill in these bonds, everything becomes stable.
So what makes these different than these?
Those are a different atom. Okay? The red ones have 2 holes in them. Okay? The red ones could represent oxygen or sulfur. Why? Oxygen and sulfur can make 2 bonds. Thank you. This is a great question. I should have mentioned this earlier, but since we were only working with the black and the yellow ones, I didn't. So if you look at the green ones only have 1 hole in them. They represent something like fluorine or chlorine or bromine. Those atoms that can only form 1 bond. That's it, because they only have 1 electron to share. Okay? The purple make 1 bond, so that's a different one. Maybe the green is fluorine and the purple is chlorine. Okay? The orange, again, 1 bond, so it's got to be a halogen. Okay? So the holes in there tell you what kind of compound it can make, how many bonds it can make.
Why is yellow 1 bond and then orange is they're 2 different?
Because there's different atoms that can all do the same thing. Hydrogen only needs 1 electron to fill its outer energy shell. So that's what this 1 bond is. It's giving it 2 electrons to fill its outer energy shell. Fluorine has 7 electrons around it. It can still share 1 bond, just like hydrogen can. Chlorine has 7 electrons around it. It could share 1 electron, just like hydrogen can. Does it a little bit differently, but it's the same basic principle. So hydrogen actually could go on top of fluorine, chlorine, and bromine because it kind of acts the same way as them. It needs 1 more electron to fill it up. Okay? Needs 1 more electron to fill it up. The reason for the 4 holes in carbon, because it needs 4 bonds to fill it up. 4 other electrons to share to fill up. Okay? And the blue ones in here, ladies and gentlemen, the blue ones in here have 4 other bonds. Okay? 4 other bonds. This one, 5. 1 on the top, 1 on the bottom. This one represents hydrogen. Okay? Because hydrogen has 5 electrons in its outermost shell that it can share. So that's why the 5 holes in here. Okay? That's why the 5 holes in here. But hydrogen gets a little bit weird. We're not going to worry about it. Okay? All right. So how many, when you put your model together, you got something that looked like this? Okay? I want you to take that last hydrogen that you put on, or that last carbon that you put on there, and see if there's another way to make this compound. See if there's a different way to put this together. So take one of the carbons off the end and try putting it somewhere else and see if you get something different while I draw out what we just drew, ladies and gentlemen, or what we just built. Sorry, some of the models have gotten a little bit old, so they occasionally will fall apart on you, ladies and gentlemen, even when you put them together good. Sorry about that. So this compound, ladies and gentlemen, again, has 4 carbons, each with 4 bonds, or 8 electrons. This model also has 10 hydrogens. Each with one bond or 2 electrons. And this is C4 H10. And it is called butane the way we have made it here. Butane is what you will find in lighters. So if you were to go to a gas station and buy a small lighter, the one that you put in your pocket, those have butane gas inside of them, or butane liquid inside. Did anybody find another way to make this? Yours and mine are the same, Greg. It's just that you've done this with it. And that's one thing you got to be careful of. If we could twist it or turn it, it would still be the same. What's different about yours and mine? Okay, so what's your original one look like? Yours is the same as mine here, Solomon. Twist it. Now, Greg did create a different one here, ladies and gentlemen. This is different from this. These are what are called isomers. These are two models that have the exact same formula, C4H10, but they have two different shapes. And what has happened is we finally got to enough carbons, ladies and gentlemen, to where we can have different shapes of the same ingredients. The same compound, C4H10. This is different than the one I have drawn here. I'm going to try to draw it up here for you, ladies and gentlemen. Okay? We're going to try to draw it up here for you. But before I do that, ladies and gentlemen, this one that I have right here would be drawn like this. Okay? 1, 2, 3, 4. Okay? And it shows that up, down, up. That is the backbone of the carbons there. Greg drew this. Or Greg created this model. He has 3 carbons in a row here. And 1 off of the middle carbon. That's what I have drawn here. Now, when you fill in, this one gets 3 hydrogens. This one gets 3 hydrogens. And this one gets 3 hydrogens. But this one here, because it is bonded to 3 other carbons, it only gets 1 hydrogen. This, ladies and gentlemen, is still C4H10. Okay? That is still the compound here. But it is not the same substance that I have. This is butane. Okay? This is called methyl propane. Okay? Methyl propane is what that is called. Okay? Now, I'm not going to ask you to name these. I'm not. Okay? But the reason they call it methyl propane is because propane is 3 carbons in a chain. And this branch here, ladies and gentlemen, is what is called a methyl branch. In other words, it's 1 carbon long. Yes, sir. Where?
No, I'm just saying, what about if you put another bench on top?
Okay, well, here's the problem. Can I borrow yours again for a second, Greg? The problem is, you want me to take off of the end and put another branch on top, right?
Mm-hmm.
Okay, well, if I take it off of here, the only place for me to put it.
No, I'm saying, get another black one.
Well, then hold on. My gosh, you haven't figured out that the bigger we make this, the more you can do?
Yeah, I realize.
Point being, though, if we take that one that Greg had here and move it, there's no way where I can move it where I don't get the exact same thing Greg had, or it goes back to being the exact same thing that I had. Those are the only two. These are the only two ways to rearrange this. Thank you very much, sir. Now you want to try another one? All right, let's try putting another one on there. Okay? Let's try putting another one on there, ladies and gentlemen. What is that used for? Okay. Since you asked, I will tell you. These, ladies and gentlemen, these springs can go into the black sears, and you can use more than one at a time. And what do you think that is? Well, this is a double bond between these two carbons. In other words, now instead of sharing one pair of electrons, they are sharing two. This is a double bond. Remember, last week, Friday, we said carbon was unique. It could make a single bond, could make a double bond, and actually, if you took one more spring, ladies and gentlemen, you could even make what is called a triple bond, like that. Okay? But real quick here, ladies and gentlemen. Notice where the last bond is here. And the last bond is here. They are facing almost completely away from each other. So this is a good molecule. The carbon has 4 bonds around it. They're sharing 3 between the two carbons. You will never get them to share 4, though. That last bond is pointing completely away from the other. There's no way that you can get it where it will ever share that last pair. Okay? So that's what these springs are for. They make what we call double or triple bonds, ladies and gentlemen. Okay? All right. So here's what we're going to do. Again, Solomon kind of jumped the gun on this a little bit. Here is my model, ladies and gentlemen. Okay? My model, again, I'm going to make the basic one. And what I mean by the basic one, this is 5 carbons right in a row. I want you to try to create different models than this out of yours. So don't do 5 in a row. All right, Greg's got one there. Okay, now, one thing for sure, ladies and gentlemen, you need to have how many carbons? Nope, you need 5 total. And then you need 3, 6, 9, 12 hydrogens for everything to be stable. And see how many different ways you can create different models, ladies and gentlemen. Okay? See how many ways you can create different models. Now, To make life a little bit easier, ladies and gentlemen, when I draw these, I'm going to stop writing the hydrogens. Only because the hydrogens kind of get in the way. So I'm going to put the hydrogens in on mine, but when I try to draw Greg's in just a minute because his was different. We're going to see if I'm going to leave off the hydrogens. So here's what I have. I have 5 carbons right in a row. Three hydrogens on the 2 ends. So this, ladies and gentlemen, is C5H12. All right. So, anyone think they have another way of doing this? Greg, I know you do. Take a look at this. Okay? You think yours is the same or different? Okay? Let's try these two. Because I agree too, they are different than the one I have drawn up, or I have up here. This is Greg's. This is Kenya's. Okay? So I'm going to try to draw these two for you. Okay, so Kenya's has 4 carbons in a row. And then off of one of the carbons, she has another. Okay? Greg's has 3 carbons in a row. And off the middle carbon, he has 2 other carbons. All right? So this one is Greg's. This one is Kenya's. Now again, Greg, 1, 2, 3 carbons. That is the longest chain, no matter how you look at this. It's 3 in a row. And that's the way we look at these, is how long the chain is. Okay? This chain is 5 carbons long. This chain is 3 carbons long, and Greg has 2 more attached to the middle. That is a different molecule than the one that I have here, definitely. Okay? Now, Kenya's has 4 carbons in a row. And then 1 off of here. Okay? Now, I want to point out, this is hers right here. Correct? If I take this carbon and put it over here on this one, all I've done is flip this around. It's not any different. Okay? I haven't taken anything off and I haven't put anything in here together again. I have just taken and flipped it. And if you can flip it, it's not anything new. What you created was new though. Greg, what you created was new. Okay? They are different than the one that I have here. So, a minute ago, we had 2 ways of doing C4H10. Now we have 3 ways of doing C5H12. Okay? So we're going to take and we're going to do one more. We're going to do C6H14. Okay? If you're losing your sears, you got to go grab them, please. Okay? Go grab them or please return them to the person who lost them. Okay? All right. Let's take and let's go one more and see how many different structures we can get if we go one more carbon, ladies and gentlemen. Okay? So one more carbon. And let's see how many different shapes we get. So I have mine up here, ladies and gentlemen. And again, I just did this straight one, the easy one. Okay? These are all C5H12 H12. And there are what are called 3 isomers, 3 different ways of doing it. There is this way, this way, and this way. So now, ladies and gentlemen, we're going to try one more. We are going to try C6H14. I'm going to quit putting hydrogens on here because, again, we can clearly see how many we have here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so if you think you have a different shape than mine here, please bring it up to the front and we will try to draw it. So if you think you have a different shape than the one I have created here, please bring it up to the front. And if not, try to create a different shape. Is this different? Okay. There's Kenya, there's mine. Are they different? Anybody else got a different shape? If everything's in a straight line, ladies and gentlemen, it's probably not a different shape. You'll notice mine, all 6 are in a row. Kenya has 5 in a row. And then she has 1 on the top in the middle. Anybody else have anything different? Can I steal this? Is that the same or different from Kenya's?
Different.
It is definitely different. It is definitely different. Let me draw these two and see if you could see the difference a little more clearly when I draw it. This is Kenya's. It has the carbon right in the middle of the other 5. This is Evelyn's. It has the carbon off of the second one, not off of the middle one. Salman, you think you got something different?
Whatever this is.
You got one more hydrogen? I'll put it on. Here, bring me one more hydrogen, please, real quick, sir. Right in there. Perfect. Salmon's is a little bit difficult to put up here, but it is actually different as well, ladies and gentlemen. 1, 2, 3, 4 carbons in a row. And he has a branch off of here and a branch off of here. So that is different than these two. Anybody else? Anyone else think they have a little different one than what we have up here? What what's happening though every time we add a carbon?
It's giving us more places to trade.
Giving us more and more different structures. The first one, there were only 2 of them that were there. Then there were 3. How many are here now? 4. Every time we're getting more and more different structures, ladies and gentlemen. Every time we're getting more and more ways to put these things together. And that is why organic compounds are so plentiful on our planet. There are so many different ways to put them together, ladies and gentlemen. So many different ways to combine the same 2 ingredients. Okay? All right. So if you would, ladies and gentlemen, I'm going to give you your models back. There you go. If you would, please start taking everything apart and putting it back. If you cannot get a stick free from one of the sears, let me know. I have some pliers. I will come over and I will help you. But please, take apart all of these sticks from these sears. Put the black sears in that shorter section over where there's fewer of them, and the yellow in the other area. And then put your sticks back in the middle, please. When you're done, bring your kit back up and throw it in the backs up here, please. Again, if you cannot get something apart, please do not just leave it together in the kit. Please bring it to me and I will help you get it apart. You may have to move the spheres around in the container a little bit to get them all into the right place, but they should look nice and even, ladies and gentlemen. So in the end, ladies and gentlemen, it should look something like mine up here before you put it away, please. And then bring it up and throw it into the box, please. Bring it here. Figure these out. There you go, sir. Thank you. You're welcome. You betcha. There you go.
Thank you.
You're welcome. Got a few?
Yeah.
Yep, the short ones are the hard ones to get out because there ain't much to grab.
Thank you.
Hang on.
Oh,
One more. There you go, sir. Thank you. All right. Okay, ladies and gentlemen, we just have a couple minutes left here. We're not going to start something new, but again, for those who weren't here at the start, here are your deadlines, here are your dates that you need to remember.